So hi everyone, I'm Guy. I'm part of the IP shipyard or interplanetary shipyard team that nucleated away from the protocol lab Stewart's team. I'm working mostly at the moment with the probe lab team, providing metrics to Web3 networks in general. And today I'm going to discuss DHT interoperability, trying to define it and see what problems it can solve with the current DHTs that we have and the future DHT that we may want in the future. So first, just a quick recap on Kademlia to have everyone on the same page. So Kademlia is a distributed hash table, which is basically an overlay network of peers that are connected to each other over the internet. And it's a distributed key value store. So you can think just a key value store, but it's in the network. And so you need to assign the key value pairs to peers in the network and to have a deterministic way to find where to allocate these key value pairs so that others can read them at the same location. So nodes are identified by a key. And so basically everything is identified by a key. Nodes, content, everything that you want to address is just a key in this key value store. That's what makes the DHT highly scalable is that you can find the content. So usually in most DHT implementation, so it's also the case in Kademlia, you can find the content in a time that's logarithmic in the network size. So if you have n peers in the network, you will be able to find the content or the peer you're looking for in log n hops or log n steps. So you will contact this number of peer. And the state you need to keep is also logarithmic. So you will need to remember a logarithmic number of peers for these to work. So there are also examples where you know everyone in the network. So the routing is O of 1, so you find what you're looking for in constant time. But that's hard to do because of the churn, so nodes joining and leaving the network. And also you need to store a big state and be updated of every change in the network. Or conversely, you can know about just a small number of peers, but it means that you will have to look up, so the lookup complexity then explodes. And in Kademlia, so the state that is stored on the node is called the routing table. And so that's where nodes remember other peers in the network and how to reach them. So in libp2p, that's storing the multi-address of the associated peer. And the routing table of Kademlia is organized into buckets. And so we'll see quickly how it works. So in this example, so we represent the Kademlia key space as linear. So it's not exactly the case, but for this example, it's good enough. And so let's take the peer, so the reference peer, at the bottom of the arrow. So it means that the nodes at the top of the screen would be far away from me, from my node, and the nodes at the bottom of the screen would be close to me. In the term, so not in a geographic term, not in ping distance, but just in the XOR metric. So each node is given a key which determines a location, and from the location we can compute distances. Now we break this key space into zones that we call buckets. And as you can see, the bucket, so the bucket 3 is, so yeah, in this representation, half the size of bucket 2, which is half the size of bucket 1, which is half the size of bucket 0. So hence the logarithmic scale. And the way we need to select peers in order to have routing soundness, so to be able to route to any key, any peer in the network, is we need to keep a constant number, so to know a constant number of peers in each of these buckets. So in this case, say we want to remember 2 peers in every bucket. So it means that for bucket 0, I have a larger choice. So there are 5 peers, and I only need to remember 2 out of the 5. Then in bucket 1, I need to remember, so there are only 2 peers, so I need to remember both of them. Bucket 2, there's only 1 peer, and it's no big deal, I just need to remember it. And in bucket 3, there are no peers and no big deal. So it means that the closer, so I will remember a lot of peers that are close to me, so at the bottom, and the further away it gets, I will remember less and less peers. So that's how the routing table of Kademlia works. Now, so the question of the state isn't only about the storage or even having it in memory. It's also about maintenance, because so you will keep a logarithmic state in memory, but you also need to make sure that these peers are actually reachable, because if you receive a request from the DHT network, you're going to respond with peers that are closer to the requested key, but you don't want to provide peers that are not responsive. Otherwise, someone is just going to time out. And so we want to avoid that. And so to keep, say, only a live peer in the routing table, we must probe the peers every so often. And we must also make sure that we know all of the peers that are close to the reference node, because that's just how you find content. So I know my closest neighbors know me. And so if nobody knows me, then nobody can be routed to me. So it's very important for peers to know their closest neighbors. And so it means that because of this maintenance, the higher state you keep on a node, the higher network load you're going to end up having also. So you want to reduce the state that you keep to a reasonable amount. And now just something to make sure we're on the same page. So to disambiguate what DHT is. So we have the DHT protocol, the DHT implementations, and the DHT swarms. So the DHT protocol is the spec layer. So it's, for instance, the lip2p cat DHT that defines the behavior of the nodes that they should have. So another example is the Ethereum discovery DHT. Then there is the implementation. DHT implementation is basically implementing the specs. So taking the lip2p specs, there are the Go implementation, JS implementation, Rust implementation, and so on. So they're all implementing the same spec. And then there is the DHT swarm, which is basically a deployment of DHT implementations. So that is nodes that are connected to each other, and basically a swarm of peer. But what's tricky is that, for instance, the Amino DHT and the Filecoin DHT are both instances of the lip2p cat DHT protocol, but they are separate network. And they use the same implementations. So they use, I don't know, maybe the Go and the Rust implementations, but they are separate networks. And yeah, it's important to remember. So multiple implementation can interact within the same swarm, but they can be distinct swarms. Now, let's get back to interop. So what is it? So we're going to try to define it and define also why we want it. So we want to be able to have interop in order to allow participation in multiple swarms. So we're going to see an example later. Or we also want to make the protocol, the DHT protocol evolves over time, because maybe there are some new needs, or so we want to be able to boot up a new DHT specification and to have it to have some interoperability with the older protocol for the time of the migration. We also want to have transport compatibility, which is really important. So it means that if I have a node that speaks only WebRTC and a node that speaks only Quick, for instance, they won't be able to communicate with each other. And so that's also a problem. With interop, we can also improve the network security and allow easier bootstrapping for new networks using already existing Kademlia networks. And also important, what we don't want to do. So we don't want to merge existing DHT, say, okay, I have the mainline DHT, the Ethereum Discovery DHT, and the Amino DHT. Let's have just one DHT for everything. So that's not what we want to do. And we don't want to force or impose a global standard on everyone, say that is the way to do DHTs. It should be more, if you want to be interoperable with other DHT, then that's how you should do it. Now quickly, so the different layers that we have within the DHT implementation is first the wire format. So once you are able to transfer data with someone, what data you're going to receive, and so we want to make sure that the implementation can just interpret this correctly. We need to have some common transport to be able to open a connection with different DHT. Sometimes there's an encryption layer that should also be supported for two nodes that would speak a different protocol. Then the identity is often used in the encryption, but also in the Kademlia layer because it determines the location of the node within the key space. And then, so the Kademlia layer, so we will focus mostly on the Kademlia layer here, is everything from the routing table implementation, the DHT lookups, so all the behavior that's actually the DHT behavior. So now let's look into a concrete example. So say I want to have a node that can interact with both the BitTorrent mainline DHT and the Amino DHT. So say, I don't know, in magnet links, we can have a CID. And when I open a magnet link, I want to just race both networks and get the data from whichever is the fastest. So I build Hexo. So Hexo will actually need to participate in both DHTs in order to be able to interact with both of them. So it means that the state it needs to keep is double, so double the cost for the maintenance, and there are also more connections to be opened, which is generally not good. But we can optimize it, and so that's what we want to do. So now, if we take the same figure as before, mainline DHT is also using Kademlia. So the DHT key space is similar, so they could be interoperable. So one requirement that is key here is that you remember before we said that the reference node, so the node say we are running, is at the bottom of the arrow, and it means that it must be, so the identity in the Amino DHT and in the mainline DHT should be the same or at a location in the key space that is, say, close enough. So that's one requirement that's a bit hard because you need to basically, if you have an identity in the Amino DHT, and in the mainline DHT, you would need to just brute force until you generate an identity that is close enough. So, yeah, and so in this case, so you will need to select peers both from the Amino DHT and from the mainline DHT, same criteria as before, so 2 peers for each bucket. And so it means that we would keep in this example 12 nodes in the end to the routing table. But now, if there's a small swarm of peers running Hexo, so participating in both DHT networks, so both Amino and mainline, and that I have an identity that's at the same location approximately of the key space, it means that instead of selecting one node running in Amino and one node running in mainline, I can just select one other Hexo node that is running in both. So, for instance, in bucket 0, I can just, so before I used to have 2 nodes in Amino and 2 in mainline. Now I can just have 2 that are running both networks. So I actually reduce the state that I need to store. And so as a result, I can just decrease the routing table size. And we can see that as the population that's running the Amino plus mainline DHT increases, I'll be able to select mostly peers that are running both, and so I'm effectively just reducing the state of the routing table that I need to keep. And so it scales very well, and so we can see that the final routing table size that I'm going to get in the end is going to be approximately, or tend to be, the size of the routing table that I would have if I was just running the largest of the two DHTs. So in this example, we can see that there are much more peers in the main line than amino. And so if I go back here, we can see that I have 7 yellow nodes. And in the end, I end up with also 7 nodes and just 1 yellow. So yeah, that's how we can optimize for selecting peers that are running in both. And also the good thing is that it can be applied for much more than just 2 networks. So it can be applied for 3, 4 networks, but also for different applications. So other use cases also include protocol evolution. So say we want to have now, in the amino DHT, we want to implement SCADemlia, which is secure for Cademlia, and it adds security against Eclipse attack by requiring nodes to solve a cryptographic puzzle when generating their identities. And so if we are to make this upgrade, for instance, it means that node would need to generate a new identity to form a new DHT networks, and then the content should be migrated over to this new DHT network. And so it means that for a while, we would have the protocol version 0, which is the DHT we're using today. Protocol version 1 is the SCADemlia, so the new network. And for some transition period, until all of the content or most of the content is transitioned to the new network, we would need to have node to retrieve content from both DHTs because the content may have migrated or not. And so we can use the same concept to optimize for protocol evolution this way. Now, another problem that we face a lot with the DHT is the transport compatibility. So Alex showed the same plot yesterday. We can see that the browser nodes have a low presence in the DHT, and that's a problem because if you want to use the DHT from the browser, you're just going to find quick or TCP peers, and you won't be able to open a connection to them. So yeah, in the amino DHT, that's really a problem for browser nodes. And the effect is that, for instance, if I'm a browser node and I want to publish some contents, say publisher provider records, I'm gonna try to interact with the DHT and find the closest peers to the key I want to put the provider records for. But as we can see, the population is quite low. If I'm using only WebRTC, then probably the 20 closest peers to the location, because I replicate the provider record 20 times, all of the nodes are not going to support WebRTC. So I won't be able to write the provider records. And same thing the other way around. If I'm looking for a provider records and I'm using only WebRTC, and the nodes storing the provider records do not support WebRTC, I won't be able to retrieve this provider record, even if in the end the provider is supporting WebRTC. And so, yeah, that's a big problem. And also, not only the transport, say quick WebRTC and so on, but there's the IPv4 and IPv6. So say if I support only IPv6, but the rest, most of the DHT is supporting only IPv4, I will be penalized for it. So we could try to do to draw the same boards that we used to have for before, but then it quickly becomes too complex because now, so if we want to use just IP4, IP6, quick and WebRTC, the number of possibilities is just huge, so we won't use the same diagram anymore. But so what it means is a node must be able to find the closest nodes that are using the same transport as they are. So if I'm using IP6 WebRTC, I should be able to find any key, so all the nodes that are running IP6 WebRTC. So it means that effectively each transport would have a sub-DHT. So there would be a sub-DHT swarm of peers that are running exactly the same transport. And nodes that participate, and nodes would participate in so many sub-DHTs. So if you support IP4, IP6, quick, TCP, you will then participate in all the combination of those sub-DHTs, and you will try to write and read from and to all of these Now let's also, so now we broke sub-DHT out of the transport, and we can also do so out of the features. So what I call features is, for instance, in the IPFS DHT, what you can use is provider record, so if you're looking for content, but you can also use IPNS, which is a slightly different mechanism. And you can also use the DHT for other stuff, say find relays, or a coordination point for hole punching and this kind of stuff. And maybe you don't want to participate in all of this. Maybe you just want to participate in IPNS and you don't care about provider records, or the other way around, which means that we can even make more sub-DHTs. So now, for instance, a node, say a Helia node that's participating, or a Kubo node that's supporting Quick, that would be supporting Quick, WebRTC, IP4, IP6, IPNS, and PROVs, which is standard for IPFS nodes, or you can even imagine more transport, would be participating now in 8 sub-DHTs. And now let's see how we can optimize the participation so that you don't need to do 8 distinct lookups for every time you want to look up for a key or every time you want to write something on the DHT. So let's introduce the multi-query, which is basically a new find node. So the way the find node RPC works is that you just send somebody, hey, I want to know closer peers to this key. And the peer will say, all right, look up in its routing table and return you closer peers. Now, what we add, so in the find nodes with feet, is a list of features. So say, I want to know so I'm using, say, IP4 and IP6 WebRTC. So I tell the node, okay, now give me the closest node that you know that are running IP4 WebRTC and IP6 WebRTC. And so in IPFS, we have a key value of 20, which means that we will have at most a response of 40 peers instead of 20 that we used to have with the normal find node RPC. But we expect to have a high overlap because maybe a lot of nodes are running both IP4 and IP6. So instead of having a response of 40 nodes, I may have a response of 24 nodes. Say that most of them are running both IP4 and IP6, and some of them are running just IP4 and some just IP6. And I will effectively have all the closer nodes for both of these transports. And I will be able to write my provider records there. So taking another example, so with the IPFS provider records, if I want to provide some content, and I will write it to all the sub-DHTs of the transport that I participate in. And it will allow all other peers whatsoever that are sharing at least one common transport with me to find the provider records and then to open a connection with me. And I can argue that I don't care about like writing a provider records on a transport that I don't support, because anyway, the person that, or the node that is going to find this provider record will not be able to open a connection to me if we don't share a common protocol, a common transport. However, it becomes a bit trickier with mutable records, such as IPNS. So for instance, if multiple peers want to write at the same key, and they support, they have different transports, it means that, so each of the nodes storing the provider records may have a different set, may see a different set of upgrades, and even using CRDTs, because you don't have the same set of upgrades, you will not end up in the same state, which is a problem that we already have today, and so this is not solving this problem. So to solve it, we would need to sync between the nodes that use different transport. Now, what are the requirements to run a sub-DHT? So basically, because it's a distributed key value store, you want nodes to be able to read and write to your sub-DHT, and for routing soundness and to be able to find the right location to write and read, you want the find node or the find node with feats RPC, and that's basically all you need to create a new sub-DHT. And actually, the sub-DHT must be as small as possible. So we should decouple the transport and the features from each other and not have like one big DHT that's doing all the possible transport and many features. Because then if a node wants to participate just in a few things or just has a few transport, you won't be able to participate efficiently. And also each sub-DHT can have its own requirements. So we can totally imagine a DHT that's permissioned, that you can participate only if you're on a whitelist. Or, for instance, you have to prove that you belong there or that you've solved the cryptographic puzzles, for instance, Academia, to be able to participate in such a DHT. Something interesting that we can have is that we can create more sub-DHTs to have more global layers. So for instance, we can have, and that's totally optional, but now we have multiple DHT swarms that are all using the lib2p specs. So you can think Amino, Filecoin DHT, Polkadot, Celestia, and so on. And maybe you want to build a cool app using lib2p and you need DHT for synchronization, but you don't want to run all the IPFS stuff. So maybe you need relays. And so what we could do is just have like a global relay sub-DHT where all the nodes from all different DHT networks that use relay can participate. And so you can find, so that would be a huge network of relays that anybody can use and join without being tied to use a specific features from other networks. Also, you can use a find feature. So a find feature sub-DHT that would allow you to find nodes that are running a specific feature. So you could bootstrap new networks, not having to, say, provide or communicate the address of a proper bootstrapper. You could use already existing network to bootstrap new DHT networks. And in order to increase security, so one main concern for DHT is Eclipse and Sybil attacks, and how it works is if you want to target one specific peer and eclipse it from the network, you just generate a lot of identities around these peers, and you pretend not to know this peer so that this peer cannot be found anymore. But now, and this can be observed by looking at the density in the key space around this peer. So you can easily detect Eclipse attack, but once you detect it, you can just not reach this peer anyway. But now, if we have a global layer, it means that it is much more harder to make Eclipse attack because you will detect that there is an Eclipse attack. And then if there is a global layer that is much larger and has much more participants than just the small DHT you are running, it becomes much more harder to generate a lot of identity because you need to eclipse the peer in the small network, but also in this global layer. And so it makes it much more expensive to run Eclipse attack. Now, if we go towards standardization, we need to so we don't really need to standardize the transport. We need to standardize, say, the RPC format, the wire format, but the transport, it's fine to use multiple transport. It's just that if you want to communicate with someone, in the end, you need to have at least one common transport, but we don't need to standardize everything. It would be great to have like one identity that you could use in all the sub-DHTs. That's true. And even if you have a breaking change, you want to make a new identity, it should be compatible with the same key space. Yeah, I already touched upon the RPCs. And so going forward, how we can get this implemented and like what could be on the roadmap. So for now, nobody's working on it. It's just like a concept. So first networks that could benefit from it, so either on the transport side, on the protocol evolution, should implement it because of their own benefits. So if it's implemented in lib2p code base, then everybody can use it. And then once it's implemented first, all other networks or new networks can just reuse the code and interoperate with the already existing network. And yes, so that's how it can happen. And so especially when multiple networks use the same code, yeah, then interop is just trivial. And then it's also possible to build bridges. So if we see application, if it makes sense, to other non-lib P2P networks, such as mainline DHT or Ethereum Discovery, I'm not sure there's an actual need for this at the moment, and that protocol evolution and transport compatibility are more important. But if there's a need, somebody can build a bridge, and the bridge can be reused by multiple applications. Yeah, and so to conclude, so Omnidex, so the Omnidex, the name of the concept, enables the optimized, so an efficient use of multiple DHT networks at once, and breaks down the big DHT networks that we currently have in multiple smaller sub-DHT networks, and makes the use very efficient. So it solves a lot of transport compatibility issues and protocol evolution issues. It can increase the security for all DHT participating in global layers. And it also allows more granular participation in smaller subsets of the DHT features without having to run a full node and participate in all the DHT feature of a network if you just want some smaller benefits. And so, yeah, that was Omnidex. So.